Hey guys, we're back and this is our last section of the year. Awesome. So let's get started. The binomial. Keep in mind, remember what a binomial is? It usually means there's two parts. We'll call this, I don't know, x and y to some power out here. So we call this is the binomial because there's two pieces in there and there's usually a power outside. So this is a theorem that helps us quickly and easily solve and expand these binomials, okay? So here's what a binomial coefficient is. It's the coefficients of binomial expansion. Okay, and just remember that if something's being expanded, like for example, if you have x plus y squared, that's like saying x plus y times x plus y, right? And before we used FOIL, which would give us x squared plus xy plus 2, well, plus xy, which would be giving me 2xy plus y squared. But what if you were doing x plus y to like the 8th? I'd have to multiply and FOIL it out 8 times, and that'd be so complex, and that's what the binomial theorem is going to do for us. The Pascal's triangle is a really fun, fast, visual way to know the coefficients or the binomial coefficients of expansion. To do this quickly, so it starts off like this, where for each degree, the coefficients, we know that every degree of 0, the coefficient is 1, right? Well, if the degree is 1, we're going to have this triangle of 1s here, where we have a 1 here. So every term of 1, because if it's binomial, right, x plus y to the 1, we have a coefficient of 1x plus 1y to the 1 power. And then as we go from there, we know a coefficient of 2 means that we're going to be adding an extra term. The coefficients on the ends are always 1, but then the next term in the middle is this 1 plus 1 is 2 in here, okay? And the way we would find the next one, if there's 3 terms, the coefficients on the outside are 1s always, and then we take the 2 above it to make the middle term. So 1 plus 2 is 3, 2 plus 1 is 3, and then it goes on, so on and so forth. And we'll create a whole Pascal's triangle later, but it does go on for infinity. So let's go ahead and list 4 general observations about the expansion of what it would look like to expand a binomial x plus y by some value of nth degree. So here's the thing. Each expansion, there are one more term than n. So we say n plus 1 terms. Number 2, that x and y have symmetric roles, meaning as they get expanded, as x decreases, y will increase, and I'll show you that in a second. That powers of x decrease by 1 successively, and powers of y increase by 1 successively. The third one is that the sum of the powers in each term is n. And then lastly, that the coefficients increase or decrease in a symmetric pattern. Okay, so here's the deal. The binomial theorem states that the expansion of x plus y to the nth power, we can say, okay, well, it's got this first power of x to the n plus n times x to the n minus 1 times y, and so on. Or we can put it in this formula, that it's some number combination of taking r things at a time. This is called a a combination that you might have seen before if you studied statistics or probability. And the way that we label this is n factorial, which we learned factorial, over n minus r factorial times r factorial. That's a lot of factorials, right? So let's go ahead and we're going to find the binomial coefficient of 12c5. So we're going to use this where n is 12 and r is 5. Okay, so here's what we're going to do. Knowing that n is 12 and r is 5, we're going to use this formula to solve this. So let's find the binomial coefficients of NC12. So here we go. What we mean by that is if there are 12 powers and we're taking the fifth value into it, what would be the coefficient of that value? So we take n, which is 12, factorial all over, n, which is 12 minus r, which is 5, factorial, times r, which is 5 factorial. So if we were to write this out, 12 factorial, 12 minus 5 over, which is 7. And remember, 12 factorial is 12, 11, 10, 9, 8, 7, and so on. What I'm doing here is I'm trying to cancel out where I can. Do you see how this, I stopped at 7 because this is 7. So what I'm going to do here is these will cancel. And I'm left with 12, 11, 10, 9, 8, all over 5 times 4 times 3 times 2 times 1. And if I plug that into the calculator, we get 792, which is the binomial coefficient of 12c5. So writing out the coefficients of a binomial that's raised to the power is called expanding a binomial. Now, before we write the expansion of this expression, I'm going to show you the next part. So go ahead and scroll down to the next page, past something called Pascal's triangle. So remember, we have our degrees. Remember, the degree is just the exponent. So we can start at 0, and then we'll have 1, 2, 3, 4, 5, 6, and so on. That if we have our coefficient, remember we're expanding x plus y to the nth. So a degree to the 0 power, anything to the 0 power is 1. And anything, so a binomial to the 1 power will have 2 coefficients of 1 and 1. So this is why we start to see this triangle effect right here. To find our second one, we always end with 1s. And we're going to fill in, okay, the middle term is going to be these two numbers and add them. So 1 plus 1 is 2. Whoops. And then now to the next one, to the third power, we start with 1, we end with 1, and now we're going to go 1 plus 2 is 3, and 2 plus 1 is 3. The next one, start with 1, end with 1, and we get 1 plus 3 is 4. Whoops. 3 plus 3 is 6. 3 plus 1 is 4 again. Keep going. I'm going to give myself a little bit extra space right here. And then we're going to have 1 starting and ending, and we're going to do our sum of our two terms above. So 1 plus 4 is 5. 4 plus 6 is 10. 6 plus 4 is 10. And then 4 plus 1 is 5. And then lastly, for our 6th degree, we've got starting and ending with 1s, and now we're going to add the sum of the top two. 1 plus 5 makes that triangle with 6. 5 plus 10, 15. 10 plus 10 is 20. Do you see a pattern? We're going to be repeating again. 10 plus 5 is 15. 5 plus 1 is 6. Do you guys see a pattern here? See how we went 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 1 is 3. And then here we went 1 plus 3 is 4. 3 plus 3 is 6. So see how it goes in a symmetrical pattern. 1 and 1 is symmetrical. 1, 2, 1 is symmetrical. 1, 3, 3, 1 is symmetrical. 1, 4, 6, 4, 1 is symmetrical. 1, 5, 10, 10, 5, 1 is symmetrical. 1, 6, 15, 20, 15, 6, 1 is symmetrical. And they increase and decrease in symmetrical patterns. So we're going to use this Pascal's triangle to actually expand the expression in our previous example to the 5th power. And let me show you how to do that. So in order to go to the 5th power, we're going to use the row right here. So to the 5th power is this row. So we know we're going to use those coefficients of 1, 5, 10, 10, 5, 1. So I'm just going to write it right here next to Pascal's triangle. So I'm going to rewrite this example 2, x plus 2 to the 5 right here, okay? So we know we're going to start off with these coefficients, which were 1, 5, 10, 10, 5, 1. And we're going to space them out right here. 1, 5, 10, 10, 5, 1. Okay, so those are our coefficients that were spaced out here. We're going to put little pluses in front of them. Now, these are the coefficients, which remember, coefficients just means they're being multiplied by something. And then this is really fun. We're going to take this term and this exponent, and those are going to go first. We're going to go x to the 5th, and then we're going to go in descending order. X to the 4th, x to the 3rd, x to the 2, x to the 1, and then x to the 0. Okay? And then we're going to take this term, and we're going to go backwards. So instead of starting at 5, we're going to start at 0. Because remember, for each group of terms, the exponents are going to add to the total exponent. So if the total exponents here is already 5, well then 2 has to have an exponent of 0 because the 5 and the 2 exponents have to add to 5. The next one, 2 to the 1, because 1 and 4 make 5. And then we've got 2 to the 2. Remember, these are all being multiplied. And remember, 3 and 2 make 5. And then we've got 2 to the 3rd, because 3 and 2 make 5. And then we've got 2 to the 4th, because 4 and 1 make 5. And then 2 to the 5th, because 5 and 0 make 5. So now we're going to just simplify for each of these terms. Well, I know for this one, 1 times x to the 5th is x to the 5th times 2 to the 0 is just 1. So this is just x to the 5th. Here I know this is 5 times x to the 4th times 2, which is 10 x to the 4th. And then we're going to go, this becomes 4 times 10 times x to the 3rd, which gives me 40 x to the 3rd. And then this becomes 8, and we've got 10x squared times 8, so we get 80x squared. And then this becomes 2 to the 4th is 16 times 5 times x. And that also gives me 80x. And then 2 to the 5th is just 32. And then x to the 0 is just 1. So we get 1 times 32 is 32. So that is that whole expansion of x plus 2 to the 5th without having to FOIL 5 times over many, many, many exponents. And if you're thinking, well, Mrs. Sells, I don't know if this is actually going to make me save time. You can try it the other way and FOIL and refoil and FOIL again 5 times over, and I promise this actually saves you a ton of time. All right, you guys, that's it for today. I'll see you back in class.